Here are the top 10 most important things you need to know about exponential functions. Must know number 1. The graph and properties of an exponential function. The general format of an exponential function looks like this. Y equals a times b to the power of x. In this equation, x and y are the variables that have an exponential relationship. A and b are constants. Let me tell you a bit more about a and b. A is the initial value of the function, and graphically, that would show up as the y-intercept. At any y-intercept, we know that the x value is 0. So in the equation, if you make x 0, this power would equal 1, leaving y to just equal a. And it's also worth noting that a can be any real number. Now let's look at b. Notice that b is the base of the power. And there are actually a couple restrictions on what the value of b can be. The b value has to be greater than 0, so that the value of the function is always a real number. And the b value can't be equal to 1, so that the function isn't just a constant function. Now I want to show you what the graph of an exponential relationship looks like. So I will do that by showing you the graph of a very simple exponential function. F of x is equal to 1 times 2 to the power of x, which could be rewritten as just 2 to the power of x. But I wanted to write this 1 here just so you could see that that's going to end up being the y-intercept, or the initial value of the function. Before I sketch its graph, let's make a quick table of values. I'll choose x values between -3 and 3, so we get a section of the graph that is a good representation of what an exponential relationship looks like. And now I have to take each of these x values, sub them into my f of x function for x, and then calculate y. When looking at this table, notice that as the x values increase by 1, there's not a common difference that the y values increase by, but there is a common ratio. To get from one y value to the next, you would just have to multiply by 2. And hopefully you can see the connection of why the common ratio of 2 is occurring. It's because the base of our power in our function is 2. This initial value is just being repeatedly multiplied by 2 an x amount of times. And then if I plot all of these points on my graph, and then connect them with a curve, I can see what the general shape of an exponential relationship looks like. But when I drew this graph, I left out one key component of it. Notice as the function is moving to the right, the y values are doubling, from 1 to 2 to 4 to 8 to 16 and so on. But if I were to think about what's happening to the y values as we move to the left, they go from 8 to 4 to 2 to 1 to a half to a quarter to an eighth. They keep getting cut in half. Are those y values ever going to get down to 0? No. It doesn't matter how many times I cut this value of 0.125 in half, I'm still going to be left with something, no matter how infinitely small. That's why there's a horizontal asymptote at the line y equals 0, which is right on the x-axis. So let me communicate using a limit why the horizontal asymptote is at y equals 0. It's because the limit of our 2 to the x function as x approaches negative infinity is equal to 0. It means this function, as x goes to negative infinity, the y values are going to get closer and closer and closer to 0. And the last main property would be this function's domain and range. The domain means the set of x values the function can take. So what can we put as the input for x into our 2 to the x function and be able to get an answer? Well, anything. And graphically, we can see that because this function goes forever to the right and also forever to the left. So our domain would be any value between negative infinity and infinity. The range, however, means what's the set of y values the function could output. So what could we get 2 to the power of x equal to? Well, notice the function is always above our horizontal asymptote. So the function is always going to have a y value that's bigger than 0. So the range for this function would be from 0 to infinity. And notice I put a round bracket at 0 because we don't want to include 0. The function can never actually be 0. It's always greater than 0. Must know number 2. Exponential growth versus exponential decay. We'll start with exponential growth. Exponential growth just means we have an exponential function that is increasing. And a function that is increasing means that as x increases, y also increases. That just means in general, the function is going up to the right. And exponential decay means we have an exponential function that is decreasing. And a decreasing function is a function that as x increases, y is decreasing. Now, remember the general format of an exponential function looks like this. Y equals a times b to the power of x. A is the initial value, and that initial value gets repeatedly multiplied by the base of the power, x times. Depending on whether a and b are positive or negative, we could get a different shaped exponential function. And in fact, there are 4 different shapes. There are 2 shapes that represent exponential growth, and 2 shapes that would represent an exponential decay. Let's look at this first graph. Notice it starts above the x-axis, so the a value must be positive. And as we move to the right, the y values are increasing. So the initial value, the a value, must be being multiplied by a number that's bigger than 1 to make it increase. So the b value must be bigger than 1. But for this graph, its initial value, its a value, must be negative because it's below the x-axis. And for that function's y value to increase as we move to the right, the initial value, the a value, must be being multiplied by a number between 0 and 1 to make it get closer to 0. If we look at these decreasing functions, the first one, a is positive, but the y values are decreasing. So that a value must be being multiplied by a number between 0 and 1. And this last shape, notice its initial value is negative, and then the y values are decreasing as we move to the right. To make them to go further in the negative direction, that negative a value must be being multiplied by a b value that is bigger than 1 repeatedly to make it go further in the negative direction. So those are the 4 main shapes. Let me do a quick example of a problem that involves both exponential growth and exponential decay. Let's start with an example about exponential growth. This example says, if you start with 1 cent and it doubles every day, how much will you have after 30 days? I know this scenario can be modeled with an exponential function because we have an initial value that is repeatedly being multiplied by 2. So I can write this in an exponential format, y equals a times b to the x. In this format, a is the initial value, which in this question is 1 cent. B is the base of the power, which for this question has to be 2 because the initial value is repeatedly being multiplied by 2. And x stands for the number of times the initial value gets multiplied by that growth factor of 2. We know it doubles every day, so after 30 days, it's going to double 30 times. So our exponent on the base of our power is 30. If I sub these values into my exponential function, I'll be able to solve for y, which is how much money I have after 30 days. When evaluating this, you're going to see the power of exponential growth. We're starting with a very small amount, only 1 cent, but we're doubling it 30 times, which is going to make that 1 cent grow to over $10 million. It's going to grow to $10,737,418.24. Let's now do an exponential decay example. This example says that uranium has a half-life of 2 years. How much of a 1,000 milligram sample will be left after 10 years? Now, in this example, this word half-life just means the amount of time it takes for a sample to be cut in half. So every 2 years, this 1,000 milligram sample, it's going to get cut in half. Well, since there's a repeated multiplication by a half, we can model this with an exponential function again. I'll just have to figure out what my parameters a, b, and x are, and then I could solve for y, which is the value of the sample after 10 years. So my initial value is what I start with, a. We know that we start with a 1,000 milligram sample. B is the base of the power. That means what are we multiplying the initial value by repeatedly? Well, we're multiplying it by a half every 2 years. So the base of our power is a half. And x, the exponent on the base, is the number of times that we need to multiply the 1,000 by a half. Well, in 10 years, how many times is it going to be cut in half? If it gets cut in half once every 2 years, we can do a little calculation. We can do the total amount of time and divide that by the half-life of the sample, which is 2. And of course, 10 divided by 2 is 5. I'll write the simplified version when I write my equation. That means this 1,000 milligram sample is going to be multiplied by a half 5 times. And when you do that, you'll be left with 31.25 milligrams of uranium. Must know number 3. how to find the equation of an exponential relationship from its graph. I can tell from the shape of the graph this looks like an exponential function. I can define the relationship between the x and y values of every point that makes up this function using an exponential function of the format y equals a times b to the power of x. I now just have to solve for what values of a and b give us the graph of this exponential function. To solve for two variables, I need two equations. If I look at the graph, there are 2 points labeled for me. Each of those points has an x and a y value. Now with each of these points, I will generate two separate equations by subbing their x and y values into this general format of an exponential function. So using my first point, my equation would be 5 equals a times b to the power of 0.5. And using my second point, the equation would be 10 equals a times b to the power of 1. And now I can use the method of substitution to solve this equation. What I'll do is, in this equation, I'll isolate the variable a by dividing both sides of the equation by this power of b. And then I can substitute that value of a into my other equation for a and then be able to solve for b. Now these powers of b are being divided using exponent rules. I know that what I can do is I can keep that power and then subtract their exponents. 1 minus a half is a half. I'll then divide both sides by 5 to get rid of that 5. And then to fully isolate b, I'll have to take care of that exponent of a half. I could get rid of that by squaring both sides of this equation. And that would tell me that 4 equals b to the power of 1, which is just b. And finally, we can take that answer for b, sub it in here, which already has a isolated. 4 to the power of 0.5 is just the square root of 4, which is 2. So we have an a value of 5 over 2, which could be written as a decimal as 2.5. And then we can see on the graph, remember the a value represents the initial value. It looks like the y-intercept is at 2.5. And b is the base of the power, which in this case is 4. So that tells you what the initial value is repeatedly multiplied by every time x increases by 1. So if the initial value is at 2.5, when x increases by 1, the y value should be multiplied by 4, which it is. 2.5 times 4 is equal to 10. So the correct equation of this relationship is y equals 2.5 times 4 to the power of x. Must know number 4. Transformations of an exponential function. The exponential function y equals b to the power of x can be transformed with 4 different parameters: a, k, d, and c. Let me start by making a list and showing you a demonstration of how each of those parameters can transform an exponential function. Let's start with a, the value we multiply the power by. If a is bigger than 1 or less than -1, it causes a vertical stretch, which I'll write as Vs, by a factor of, which I'll write as BAFO, the absolute value of a. But if a is between -1 and 1, it actually causes a vertical compression by a factor of the absolute value of a. And if a is negative, so if it's less than 0, there's going to be a vertical reflection across the x-axis. The other type of vertical transformation is caused by the c value that's added after the power. If c is greater than 0, the function shifts up, and if c is less than 0, the function shifts down. And now let's talk about the horizontal transformations, which are up in the exponent k and d. If k is bigger than 1 or less than -1, there's actually a horizontal compression by a factor of 1 divided by the absolute value of k. And if k is between -1 and 1, it's actually a horizontal stretch by a factor of 1 over the absolute value of k. And if k is negative, so if it's less than 0, there's a horizontal reflection across the y-axis. And lastly, the d value is what we are subtracting from x. If d is positive, it shifts the function to the right, but if d is negative, it shifts the function to the left. Let me make a little bit of room here so we can do an example where we graph a transformed exponential function. We are asked to graph this transformed exponential function, It's a transformed 1/2 to the power of x function. We have these three parameters which are causing transformations. The number in front of the power is the a value. So the a value of -2 is going to cause a vertical stretch by a factor of 2 and also cause a vertical reflection. To do those two transformations, I'd have to multiply the y values by -2. The d value is what we subtract from x in the exponent. We are subtracting a 3, which means the d value is 3. A positive d value shifts the function to the right. So this is going to shift right 3 units. And we could accomplish that algebraically by adding 3 to all of the x values. And lastly, after the power, we're subtracting 2, which means the c value is -2, which based on this criteria tells us the function will be shifting down 2 units. And we could do that just by subtracting 2 from all of the y values of the points that make up the function. So now all we have to do is do these transformations to a set of key points for what we call the base function, 1/2 to the power of x. So I'll make a table of values for 1/2 to the power of x. I'll choose x values just between -2 and 2, and then calculate the y values by subbing my x values into my function for x. And now I'll apply my transformations to these points. And now I'll make a table of values for my transformed g of x function. In the table, I'm going to communicate these transformations that I'm doing to my x and y values. To the x values, I just have to add 3, and to the y values, I have to multiply them by -2 and subtract 2. So I will do these transformations to these points. To each of these x values, I have to add 3, and to each of these y values, when I sub them in here, I have to multiply them by -2 and subtract 2. And then I can just use these points to get a good graph of my g of x function. So I'll plot all the points. My last point doesn't fit on my graph, but that's okay. But I do have to add where the horizontal asymptote is. Remember, the horizontal asymptote of an exponential function starts at the x-axis. But the c value of the function, in this case -2, will shift the horizontal asymptote down 2 units. So the horizontal asymptote of this function is at y equals -2. And then I'll connect the points on my function with a smooth curve, showing that it's going to be approaching that horizontal asymptote as x approaches infinity. Must know number 5, inverse of an exponential function. Let's say we have the exponential function f of x equals b to the power of x. Then the opposite of that function, which mathematically we call the inverse, and we have a notation for the inverse that looks like this, where this -1 that looks like it's in the exponent doesn't actually act like an exponent. This does not mean 1 over f of x. It doesn't mean the reciprocal. It means the opposite of f of x. And the opposite of b to the power of x is log base b of x. But what is this log function? What does that mean? Well, just like division is the opposite of multiplication, a log function is the opposite of an exponential function. It undoes exponentiation. Or another way of saying that would be that a log function finds the exponent to which the base must be raised to make it equal to the argument. In that definition, I use 2 terms that you have to know: base and argument. The base of a logarithm is here. It's a subscript b, and the argument, in this case, is the x. And what this means is that if we have a log function, y equals log base b of x, the answer to this logarithm is the exponent that would go on the base of the logarithm to make it equal to the argument of the logarithm. So I could rewrite this in an equivalent way, in exponential form, by writing that b to the power of y is equal to x. Let's see if you understand logarithms by doing a couple quick examples. The first example just says to evaluate a couple logarithms. If I want to evaluate a logarithm, I just need to figure out what exponent goes on the base of the logarithm to make it equal to the argument. Well, I know 2 to the power of 3 is 8, so the answer to this logarithm is 3. And then for this one, I would be looking for what is the exponent that goes on 3 to make it equal to 9. Well, I know 3 squared is 9, so the answer to that logarithm is 2. And let's actually evaluate one more. What if we have log of 100? I don't see a base on this logarithm, which means it's the common logarithm that has a base of 10. So what exponent goes on 10 to make it equal 100 is 2. 10 squared is 100. And now let's do one more example where we can see when a logarithm is going to be useful. This example just says to solve this equation for x. 5 to what exponent equals 20? To get an approximate value for it, we can make use of the logarithmic function. We can take the exponential form that we're given, and we can rewrite it in an equivalent logarithmic form. If I'm looking for the exponent that goes on 5 to get 20, that exponent, I can get an approximate value for it by doing log base 5 of 20. And then you could use a calculator to get an approximate value for this, and you would get about 1.86. Must know number 6, solving exponential equations. Let me give you two exponential equations that we'll solve. Both of these equations look similar. We have a power equal to a power, and our unknown, x, is in the exponent. That's why these are called exponential equations. To solve these two equations, we'll use two different strategies. The equation on the left, it would be easy to rewrite those powers so that they have the same base. When I look at the bases of the powers, 9 and 27, I recognize that those are both powers of 3. I could rewrite the 9 as a 3 squared, and I could rewrite the 27 as a 3 cubed. And then on both sides of this equation, I could simplify using exponent rules. On the left, I have a power of a power. The exponent rule tells me that I can multiply the exponents together. So this becomes 3 to the power of 2 times x plus 1. And don't forget that 2 will multiply by both the x and the 1. So it becomes 2x plus 2. And then same thing on the right. I can multiply 3 by 2x minus 5 to get a new exponent of 6x minus 15. And now that I have a power equal to a power, where the bases of the power are equal to each other, I know the equation could only be true if the exponents were also equal to each other. So we can now set the exponents equal to each other and solve for x using inverse operations. I'll bring my variable terms to the right and my constant terms to the left. And then collecting my like terms, I have 17 equals 4x. And if I divide the 4 to the other side, I figure out that x equals 17 over 4, which as a decimal is 4.25. Now let's look at the second equation. It would not be easy to rewrite 5 and 7 as powers with the same base. So instead, we'll use a different strategy. We'll make use of the log function. We'll start by taking the logarithm of both sides of the equation, and then using some log rules, we'll be able to solve this equation. And if you're not familiar with rules for logarithmic functions, make sure you check out my top 10 video on logarithms as well. One of the rules you can use for logarithms is the power rule of logarithms. That tells you you're allowed to take the exponent of the argument and write it as the coefficient of the logarithm. So we can do that to the logarithms on both sides of the equation. And then we expand both sides of the equation. So do x times log 5 plus 3 times log 5 on the left. And on the right, 2x times log 7 minus 1 times log 7. I want to get the terms that have a variable on the same side of the equation. So I'll get my variable terms to the right side of the equation and my constant terms to the left side of the equation. And then since both terms on the right both have an x, we could common factor that x from both terms. And then to isolate x, I would just have to divide this constant value to the other side of the equation. Now at this point, you could type this expression on a calculator to get an approximate answer for x, but if we wanted an exact answer for x, we could use some logarithm rules to simplify this. This 3 could be moved as the exponent on the argument of the logarithm, making it log of 5 cubed, which is log of 125. And in the denominator, same thing with this 2, I could write it as the exponent on the 7, and 7 squared is 49. And now I can use the product and quotient rule of logarithms to simplify further. When adding logs with the same base, we can write them as a single log by multiplying the arguments. 7 times 125 is 875. And when subtracting logs with the same base, you can write them as a single log by dividing the arguments. So that would become log of 49 divided by 5. And then we could combine those into a single logarithm using the change of base formula, but I think I'll leave it like that, and then also just write the approximate value of this, which is about 2.97. Must know number 7, exponential equations of quadratic form. Well, what's an exponential equation of quadratic form look like? Let me show you the general structure. In this equation, a, b, c, and d are all constant values, and our unknown, our variable, is x. Notice in this equation, I have two powers that have the same base. The base of both of those powers is b. And the exponents, one of them is x, and the other one is 2 times x. When you have this structure of an exponential equation, we can solve it by first letting u equal b to the power of x. And then once you do that, you'll have a quadratic equation that you can solve. And once you have those solutions for u, you can back sub to solve for x. So let me show you what that looks like with an example. Now in this example, I have two powers that have the same base. Their bases are both 5. And the exponents, one of them is x, the other one is 2x. So I know that I can use these steps. And to make it clear as to what I'm going to be doing, I'm actually going to start by rewriting this power. Instead of writing it as 5 to the power of 2x, using an exponent rule, I know I could rewrite this as 5 to the power of x squared. And now notice here and here I have 5 to the power of x. So what I'm going to do is I'm going to let u equal 5 to the power of x. And when I replace both of these with u, my equation becomes u squared plus 8u minus 20 equals 0, which looks just like a simple quadratic equation to solve. I could even solve it by factoring. Just find numbers who have a product of negative 20 and a sum of 8. And the numbers that satisfy that product and sum are 10 and negative 2. So I know this would factor to u plus 10 times u minus 2. And this product would be 0 if either of the factors were 0. This factor would be 0 if u is negative 10, and this factor would be 0 if u is 2. But remember, we're not actually trying to solve for u. In the original equation, our unknown is x. So we have to now back sub these answers into our let statement. Each of these u values actually equal 5 to the power of x. So I'll make two equations. I know 5 to the power of x equals negative 10, and 5 to the power of x equals 2. And then I'll solve both of these equations. This equation, I'm wondering what exponent goes on x to get negative 10? Well, no matter how many times you multiply 5 by itself, it's not going to become negative. The range of this function is between 0 and infinity. It's always above 0, so there's no way it could be negative 10. So there are no real solutions to that first equation. But this second equation, there is an exponent we can put on 5 to make it equal 2. And we could find that exponent using a logarithm. If we want to know what exponent goes on 5 to get 2, I know that log base 5 of 2 would solve for that exact exponent. So x would equal log base 5 of 2. And then you could evaluate that to get an approximate value, and you would figure out that x is approximately 0.431. Must know number 8, compound interest. This is one of the main applications of exponential functions, is the ability to calculate compound interest. And to calculate compound interest, we can follow this formula, where in this formula, A stands for the future amount, P stands for the principal amount, which is just the amount you start with, I stands for the annual interest rate, N stands for the number of times interest is compounded each year, which we call the number of compounding periods, and T is the number of years. So basically how this formula works, if we know we have a principal amount that we invest in an account for T years at a given annual interest rate, and we know that that interest is compounded N times each year, we can use this formula to find the future amount of the value of the money in that account. So let's do an example. You invest $100 in an account that pays 5% interest per year. How much will you have after 10 years if A, the interest is compounded annually, or B, the interest is compounded monthly? Let's start with part A. If we want to calculate the amount in the account after 10 years, I can find the amount after 10 years by taking my initial investment of $100 and multiplying it by 1 plus the annual interest rate, which is 5%. Now, when we sub that into our formula for the interest rate, we have to sub it in as a decimal value. So 5% means 5 out of 100. So 5 divided by 100 is 0.05. And then I have to divide that by n, the number of compounding periods in a year. Well, it's only compounded annually, which means it's only compounded once a year. So I'll divide that by 1. And then my exponent is the number of compounding periods times the number of years the money is invested for. Well, the number of compounding periods in a year is 1, and it's being invested for 10 years. And then it's just a matter of evaluating. If you evaluate this, you would figure out that your $100 has increased up to $162.89. But what would happen if we compounded this interest monthly instead of annually? Well, a lot of the equation is going to look the same, except for the number of compounding periods in a year. It's no longer just going to be 1, it's going to be 12. So I'll rewrite that same equation, but change n to 12. So if we compare this to part A, in part A, we got the whole 5% interest 10 times. But now in part B, we're only getting a 1/12 of the 5% interest, but we're getting that 120 times. So you're getting a 1/12 of the interest, but you're getting it 12 times more times. Now that sounds like that should be the same thing, but you have to take into account every time you get interest added to your principal amount, your next interest calculation is going to be interest paid on top of the interest you've already earned, which is going to mean that the higher the number of compounding periods, the higher the value is going to become. And in this case, the amount after 10 years would be slightly higher. It would be up to $164.70. And as you keep increasing the number of compounding periods, this value is going to keep getting higher. But what would happen if this value approached infinity? That's going to lead us into our next section. Must know number 9, the natural exponential function. Let me start by giving you the definition of the natural exponential function. The natural exponential function is the function e to the power of x. And what's the value of e to the power of x? Well, the definition for that is that it's the limit as n approaches infinity of 1 plus x over n to the power of n. Now this formula looks really similar to our compound interest formula. And to help you understand the value of e, we can think of it in terms of compound interest. So let's say we were trying to evaluate e to the power of 1. Well, we would just write that as e, and we would calculate it by doing the limit as n approaches infinity of 1 plus 1 over n to the power of n. Right, I replaced x with 1. And I'm actually going to add another number in here. Let me add a number in front of this power. Let me just put a 1 there to keep it equivalent, but so that you can notice that we can think of this one as our principal investment, and we're getting paid an annual interest rate of 100%. Right, 100% would be 1 as a decimal value. And let's say we're just investing this $1 at 100% interest for only 1 year. And from the last section, we know that as we increase the number of compounding periods, that's going to increase the value of this power. But what will be the limit of this value as n approaches infinity? This value is not going to go to infinity. It's going to go to an irrational number that we call e, which stands for Euler's number. And I'll write down the approximate value of e for you right here. Now this value e is what we call Euler's number. It keeps on going forever with no patterns or repeats. So it can't be expressed as a fraction, which means that e is an irrational number. And another thing I want to note is that when we make the base of a logarithm e, we call it the natural logarithm, and our notation for that is ln of x, the natural logarithm of x. And now let me quickly show you what the graph of e to the x looks like and do an example that involves e to the power of x. Let's start with the graph. So for the function y equals e to the power of x, let me make a quick table of values and then do a rough sketch. I'll just choose a few x values, -1, 0, and 1. Calculate the y values by subbing these in for x. And if I were to sketch this function's graph, just like all other exponential functions, there's going to be a horizontal asymptote at y equals 0. And then if I were to roughly plot these points and connect them, I would get this shape. And now let's do an example involving the natural exponential function. Let's say we wanted to solve the equation 20 equals 3 times e to the power of x. My unknown is in the exponent, so this is an exponential equation. I'll start by isolating that power by dividing the 3 to the other side. And then if I want to know what exponent goes on e to make it equal to 20 over 3, I know I could calculate that exponent by doing log base e of 20 over 3. And then notice what I have, log base e, is what we call the natural logarithm. So I could rewrite this as the natural logarithm of 20 over 3. And then you could get an approximate value for that using your calculator. It would be 1.897. Must know number 10, the derivative of exponential functions. Let's say we wanted the derivative with respect to x of the exponential function b to the power of x. The derivative rule for this tells me that the derivative of b to the x would equal b to the power of x times the natural logarithm of the base of the power b. So you just keep the power exactly as it is, then multiply by the natural logarithm of the base of the power. Let's do two examples where we would need this rule. Let's find the derivative of 3 to the power of x, and then let's do another example where we calculate the derivative of the natural exponential function e to the power of x. Well, for the first example, if I want to differentiate 3 to the power of x, the derivative rule tells me to keep the power exactly as it is, and then multiply by the natural logarithm of the base of the power. So multiply by the natural logarithm of 3. That's it. There's the derivative of that function. And following those same rules for the second example, I can keep the power exactly as it is, and then multiply by the natural logarithm of the base of the power. And the base of the power is e. And then what is the natural logarithm of e? Well, the natural logarithm of e, remember the natural logarithm just means we have log base e of e. And if you understand logarithms, that expression means what exponent can you put on e to make it equal to e? Well, the answer to that would just be 1. So this whole expression right here, the natural logarithm of e, is actually just 1, which means the value of this is e to the x times 1, which is just e to the power of x. That's the most fascinating thing about the natural exponential function. Its derivative is itself. And now let's make it a little bit more difficult. Let's say we're finding the derivative with respect to x of an exponential function where the exponent isn't just x, it's a function of x. So for that, you would need the chain rule. And that would tell you to keep the power exactly as it is, multiply by the natural logarithm of the base, but then based on chain rule, we would then have to multiply this by the derivative of the function in the exponent. So we would then multiply by f prime of x. So we'll do one example of this, where we find the derivative of the function 5 to the power of 3x plus 1. The derivative rule tells me to keep the power exactly as it is, multiply by the natural logarithm of the base, and then because in the exponent I have a function of x, I then have to multiply by the derivative of that exponent. The derivative of 3x plus 1 is just 3. If you made it to the end of the video, good job. Hopefully it helped you out. And let me know in the comments what you want a top 10 of next. Jensen Math!